Today we will learn how to find solution of linear programming problem. Before this, we will see some of the definitions which are related to the solution of LPP. First one is a solution of LPP. So a set of values of the decision variables x1, x2, x3 and so on xn, which satisfies the conditions of the given linear programming problem, is called as a solution of that problem. So whatever values we are getting for the variables, those values which satisfies the given conditions, all the conditions, then that points are called as a solution of the linear programming problem. The next definition is a feasible solution. A solution which satisfies the given constraints is called the feasible solution. Okay, any point from the feasible solution which satisfies the constraints of the constraints is called as a feasible solution. Now what is meant by optimal feasible solution? A feasible solution which maximizes or minimizes the objective function as per the requirements is called the optimal feasible solution. Optimal feasible, optimal means either maximum or minimum. The feasible region, the common region determined by all the constraints of the LPP is called the feasible region. Then the linear programming problem can be solved by two methods. One is a graphical method and other is a simplex method. Now for this year, we will consider only graphical method. We don't have to study the simplex method. Now there are two theorems related to this LPP. The first one is the set of feasible solutions of the linear programming problem is a convex set. Already we have studied the definition of the convex set. So the feasible solution is a convex set. The objective function of the LPP attains its optimum. Attains its optimum means either maximum or minimum, at least at one of the vertices of the convex polygon, which is known as the convex polygon theorem. Now, we will see the first method. There is a corner point method. What is meant by a corner point method to find the solution of the given linear programming problem? First of all, we will convert all equations of the constraints into equations. Okay. Then in next step, we will draw the lines in the XY plane. In third step, locate the common region indicated by the constraints. This common region is called as a feasible region. And fourth one, find the vertices of the feasible region. After that, we will find the values of the objective function at those vertices of the feasible region. This is just an example. This is an example to show, to discuss the whatever the definitions we saw just now. Okay. And the problem is of either maximize or minimize. Maximize z is equal to 2x plus 5y or minimize z is equal to 2x plus 5y. Subject to 3x plus 7y less than or equal to 5, 6x minus y is greater than or equal to 13, x is positive, y is positive. Here, this z is called as an objective function, which is to be maximized or minimized. This z is called objective function. These inequations are called as constraints. These inequalities, linear inequalities in two variables, these are called as constraints. And this x is positive, y is positive. These two equations are called as non-negative restrictions. Non-negative restrictions. Now let us see isoprofit. This is the first method is corner point method. The other one is isoprofit. In isoprofit, what we are doing after plotting, okay, suppose this is z and these are the constraints. So what we will do, we will plot the graphs of these constraints. 3x plus 7y is equal to 5, 6x minus y is equal to 13. We will plot these two lines, and then less than or equal to, greater than or equal to, according to the region, we will locate the common region. So whatever common region we will get, that region is called as a feasible region. So this region is called as a feasible region. Okay, then we will take any point from this feasible region. What we will do, we will take any point from this feasible region and we will put that in this objective function. We will find the value, we will get the value of z. So by taking the value of z, we will get a line 2x plus 5y is equal to some value, that is z. That is called initial profit line. Initial profit line. We will plot it by just dotted line. Initial profit line or Z1 or Z0. Then we will go away from the origin. We will go away from origin by drawing the parallel lines to Z1, initial profit line. Then at certain stage, the line will touches only one point of this feasible region. That is nothing but our solution. This is iso profit. The second one is iso cost method. Iso cost method. In this, what we doing? Again, we are finding the feasible region. From the feasible region, we will take any one point. We'll put that point in the objective function. We'll find the value of z. Then we will draw the first initial cost line. Then we will draw the parallel lines to that lines towards the origin, so that we will obtain point of the corner points. Okay, which is the solution of the given problem. So the problem is of minimization type. So we go draw by drawing the parallel lines towards the origin. For maximization, we go away from the origin. Now, let us see one of the solved example. Solve graphically the following LPP. Maximize z is equal to 9x plus 13y subject to 2x plus 3y less than or equal to 18. 2x plus y is less than or equal to 10. X is positive, y is positive. So how to solve the linear programming problem? It is very simple. To draw the graph of the constraints, we prepare the following table. Now you must know what are the constraints. Okay, so these are the constraints and these are the non-negative restrictions. So to draw the graph of the constraints, we prepare some table. How to prepare the table? Just take the inequation. These are the inequations. Then corresponding equation 2x plus 3y is less than or equal to 18. I have written then 2x plus 3y is equal to 18. Now we must get 2 points on the line so that we can draw the line. So how one can convert these in the form of double intercept form, like by 2x upon 18 plus 3y upon 18 is equal to 1. So x upon 9 plus y upon 6 is equal to 1. So we get the first point 90. First point is 90 and the second point is 06. The second point is 06. So these are the points on the axis. Similarly, find the for the second line. But before this, what you have to do, when you have come to this point x and y for the first line, immediately plot that line. Immediately plot that line. 2x plus 3y is less than or equal to 18. That is 2x plus 3y is equal to 18. Just draw that line on the xy plane. Okay, then what we have to do, this line will make two parts of this plane. This is the first one and this is the second one. One of the part contains the origin. Now here is less than or equal to, so definitely origin will satisfy this inequality. 2 into 0 is 0, 3 into 0 is 0. So 0 plus 0 is 0 and 0 is less than or equal to 18, which is true. So the solution set lies below this line. Okay, solution set lies below this line. Now moving further, the next line, we have to plot the next line. 2x plus y is less than or equal to 10. So corresponding equation is 2x plus y is equal to 10. Again, what you can do, you can write its double intercept form like this. X upon 10 means 2 upon 5. So x upon 5 plus y upon 10 is equal to 1. So the first point is 5 0. Look at this point. And the second point is 0 10. So this is the second point. Then what we will do, we will just plot a line which passes through these 2 points. Now again, this line divides the xy plane in two parts. Okay, so one of the part is contains the origin, another part doesn't contains the origin. Again, here is less than or equal to, so it satisfies this equation satisfies the origin. 0 plus 0 is less than or equal to 10. Again, this part is lies below this line. So that's why I have written is origin side of the line. What is the region? Region is origin side of the line. Here is also origin side of the line. And this non-negative restrictions will tells us that the region lies in the first quadrant. So first quadrant means above this x-axis and to the right of this y-axis. So we conclude that the common region is this. This is the common region. Once you plot this shaded part is nothing but the common region. It is also called as the feasible region. This is called the feasible region. Now, once you got the feasible region, our next work is to find the corner points. So, what are the corner points? 0, this A, this B, this C, these are the corner points. So in what we will do now, we will state the feasible region. The common shaded region O, A, B, C, O is the feasible region. Also we called as them as a corner points of the feasible region. These are the corner points. So our next work is to find the coordinates of these corner points 0, A, B, C, O. Now we have the corner points O as origin 0 0, A 5 0, C 0 6, but we don't have the points of this B. So how to obtain the coordinates of the point B? Now B is the point of intersection of these two lines. So if we solve these two lines simultaneously, then we will get the points of the coordinates of the point B. Now let us see. The corner points are A is 5 0, origin 0 0, C 0 6. Now to find the coordinates of the point B, solving equation 2x plus 3y is equal to 18 and 2x plus y is equal to 10. We have to solve these two equations simultaneously. Now solve these two equations simultaneously. You will obtain x is equal to 3 and y is equal to 4. Now how to solve the equations simultaneously, you know better, or I will explain one here. The first equation is 2x plus 3y is equal to 18. So multiply the second equation by 3. 6x plus 3y is equal to 30. Take their subtraction. So 2x minus 6x is minus 4x. These two will cancel to each other. Then 18 minus 30. 18 minus 30. What you will get? 18 20. So you will get minus 12. So for minus 4x minus 12 implies x is equal to 3. So x is equal to 3. Now put x is equal to 3 in any one of this equation. You will get value of y. So we get the coordinates of the point B. Now we will find the value of the objective function at these corner points. So these are the corner points and this is the objective function. What is the objective function? Z. Z is called objective function. 9x plus 13y. Now at origin, that is Z0. 9 into 0 plus 13 into 0. So 0 plus 0 is 0. Now a at 50, z at a, value of the objective function at a is 9 into 5 plus 13 into 0. 9 5s are 45 plus 0 is 45. Similarly, find the value at b. Similarly, find the value of the objective function at the point c. Now, our problem is of maximization type. So we have to look for the maximum value at these corner points. So where we got the maximum value? It is 79 and at the point B. So from the table, maximum value of Z is 79 and which occurs at the point B 3, 4. That is when x is equal to 3 and y is equal to 4. So this is the corner point method to solve the given linear programming problem. This is the first example. Now look at the second example. 5x plus 2y, objective function, minimize z is equal to 5x plus 2y and subject to 5x plus y is greater than or equal to 10, x plus y is greater than or equal to 6, x is positive, y is positive. So what we have to do to draw the graph of the constraints, prepare the following table. So these are the inequations. First of all, we will consider the first inequation, 5x plus y is greater than or equal to 10. Then corresponding equation, 5x plus y is equal to 10. Now we have to find the 2 points on the axis. For that, we put x is equal to 0, you will get y. If then we will put y is equal to 0, we get x. So these are the 2 points on the axis. Then what we will do, we will plot the graph of these lines on the xy plane. Now how to plot? This is 5x plus y is greater than or equal to 10. So this is the line. This is the first line. We now we origin, if you put the origin in this line, 0 plus 0 is greater than or equal to 10, which is not true. So the side, this doesn't contain the origin side. So this is the solution set which lies above this line. Now similarly, plot the other line x plus y is equal to 6. So this is the line x plus y is equal to 6. Now here also origin doesn't satisfy this line. So we have to take the region which lies above this line. Okay. Now the next condition is given that x is positive and y is positive. Now x is positive means and y is positive means the area lies in the first quadrant only. So all, if we link all these inequalities together, you will get this shaded part of the region. This is called the feasible region. The shaded part is our feasible region A, B, C. This is the feasible region. Now we have the coordinates of the point A and C, but we don't have the coordinates of the point B. Now how to find the coordinates of the point B? This B is a point of intersection of 5x plus y is equal to 10 and this 6 plus y is equal to 6. So we have to solve them simultaneously. We will obtain the coordinates of the point B. X is equal to 1 and y is equal to 5. In next step, what we will do, we will find the value of the objective function at these corner points. The objective function and their its values. Okay. Now the problem is of minimization. So we have to think of, we have to check whether at which point the objective function is minimum. Here at A value is 30, at B the value is 15, and at values at C the value is 20. So minimum is at B 15. From the table, the minimum value of Z is 15 and it occurs at the point B 1, 5. This is our second example. Now, at the third example, similar to the previous one, maximize z is equal to 3x plus 4y, subject to these are the constraints. we have to take the inequations, then corresponding equations, then we have to take 2 points on the line. We will plot these 2 points on the graph, and then we will join by a straight line passing through them. Okay, then think of the region which lies below or above the line. Then from the graph we can see that the common shaded area is the visible region is unbounded. Okay, this region is unbounded, and the problem is of maximization. So whenever you go away from the origin, you'll get maximum and maximum value. It will never stop. Okay, so the area of the visible region is unbounded. In such case, the isoprofit lines can be moved away from the origin indefinitely. I told you that there is one another method, iso profit method for maximization, iso cost method for minimization. So here that line will go away from the origin, so indefinitely. So there is no maximum value of z within this feasible region. If the problem is of minimization type, definitely we would have obtained the minimum value. But here in this case, it is not possible to find the maximum value for the given problem. So there is no finite maximum value of z within the feasible region. Now solve graphically the following LPP. The fourth one, maximize z is equal to 5x plus 2y subject to 3x plus 5y is less than or equal to 15, and 5x plus 2y is less than or equal to 10. X is positive, y is positive. So again, first step, to dot the graph of the constraints, prepare the following table. So these are the constraints only. We are considering the constraints as equality. Okay, then we are finding the points on the axis. It is it is the simplest way to find, to draw the line. Once you plot the lines, just decide the region. This whenever there is a less than or equal to, the origin satisfies it, so we can take the origin side. In both the cases, we have to take the region which is towards the origin side, and the final two inequalities says that the region lies in the first quadrant. So this is the required region. Here 0 means O A B C O is the our feasible region. O A B C O is the feasible region, and we have the coordinates of the point O, coordinates of the point A, coordinates of the point C. Okay, so to find the coordinates of the point B, we have to solve the two equations simultaneously, which are 5x 3x plus 5y is equal to 15, and 5x plus 2y is equal to 10. These two equations, after solving simultaneously, you will get x is equal to 20 upon 19 and y is equal to 45 upon 19. Okay, so just go, this is we will put these values of the corner points in the objective function, and we'll get the values. So the maximum value of z occurs at point A as well as the point B. So at these 2 points, we get the maximum value 10. So we conclude that at every point which lies on the line segment AB is a solution of the given problem. Oh, sense. So there are infinite number of optimal solutions for this problem, infinitely, which lies on the line segment any. So any point on the line segment AB is the solution of this linear programming problem. Okay. Now we will stop here. In next lecture, we will see the problem from exercise 7.4. Okay.